Luiz, the other Luiz, in the room? Yeah, Luiz Lara.
Eu tô aqui. Deixa eu fechar a apresentação para você fazer a apresentação.
Vai lá,
E
põe o
depois
título.
eu. Não, depois eu abro de novo. O
Tá,
título, tá.
o título.
Então tá. Tá bom, então. Então eu vou abrir. Tudo bem, pessoal? Como é que tá aí? Todo mundo. Todo mundo aí. Então tá. Assim eu cumprimento o pessoal, eu vou voltar a apresentar aqui. Todo mundo vivo? Então tá bom.
Todo mundo viu. Okay, so the talk will be in English. There will be the usual announcement. So let's begin officially. So in the name of the organizers, Paolo Piccioni, Adriana Andrada, Juliet Saavedra, and myself, let's start the 2021 series of the geometry webinar. I think we can all agree last year was an exciting stretch. We had a large number of very good talks. I was very pleased with a lot of public. Let's begin the year with a high-level speaker to live up to that expectation that this year will be equally fun. A few remarks in order. So last year, you remember our talks were alternating between Thursdays and Fridays. This year, we're going to have fortnightly talks. So we're going to have talks every 2 Fridays. The calendar will be available on our website. As soon as future talks are scheduled, they will be made available there. You will find pretty soon on the chat the usual instructions to join our mailing list or to join our WhatsApp announcements group. Please feel free to just follow those instructions. If you have any questions, the speaker, there they are. You can check our calendar, future talks, and previously recorded talks on our YouTube channel. Now, if you want to join the WhatsApp announcements group, you can just click that link if you're using WhatsApp web, so you don't have to send me a WhatsApp message anymore. We've improved on that service. So as usual, the talk is being recorded. If you are appearing on the camera, just be aware that you're being recorded, and it'll be made available on our YouTube channel. Without further ado, so Luiz will give us a 50-minute talk, and then we can have another 10-15 minutes discussion. Luiz will not be able to see you while he's speaking because he'll be sharing his screen. So if you want to ask questions, you either intervene directly on the mic, or you can raise your hand, and I will mediate the questions. I'll be following up with that. Okay. So Luiz, thank you very much. So we have Professor Luiz San Martin, my very senior colleague from the maths department at UNICAMP. He's the major player in the sort of South American Lie theory scene. He's one of the patriarchs of this topic in the region, with 1 million former students working on this and 1 trillion papers about it. Still very active doing new stuff. So I think this is the right way to begin this seminar series by having him point the directions in the theory for the next year. Please go ahead, Luiz. Welcome.
Okay, thank you very much, Henrique. And well, thank you for the organizers for this invitation. I think this kind of, and for the organization of these meetings. In these times, overwhelming times we are suffering, this kind of initiative is essential to keep the community tired and the society tired, and and to do things we like, to do mathematics. The title of I prepared is maybe a bit optimistic, symplectic geometry. I have been working for some time, since 5 or 6 years ago, with these adjoint orbs. I will explain how I started with it. And I had, just at this moment, I am working with other kind of things. So what I did when Henrique invited me was to join some of the files I have in my computer, and I got some results may be disconnected ones. So I hope to not to be too much disconnected. So I try to talk 50 minutes about this subject. To start with, I will start with the basic. El básico, with are the adjoint orbits. Sorry. The adjoint orbits of non-compact semisimple Lie groups. Actually, semisimple Lie algebras. The group is a bit immaterial. When you have a, can you see my cursor or not? I am asking.
Yes. Yes.
Yes. If I mark here, it's better.
It's readable. Yeah, we can see it.
Yes. The blue ones. Okay, I will put the blue ones to indicate what I am talking about. You start with a semisimple Lie algebra G, a non-compact semisimple Lie algebra. In principle, it can be real semisimple Lie algebra. The basic structure of the semisimple Lie algebra is the so-called Cartan decomposition, which is a K. I write it as a Gothic K for compact and a Gothic S for symmetric. This is the and maximal abelian subalgebra in the symmetric part, and this nilpotent component with this n. And I wrote it here just to write for the first time the roots of the Lie algebra. This nilpotent subalgebra is the sum of the root spaces for positive roots, or for a given choice of positive roots. The example, the guiding example, I will always use it when in classes, is this decomposition where I write the Iwasawa decomposition. The compact part is the skew symmetric matrices. The A part is the diagonal matrices, while the nilpotent part are the upper triangular matrices. Here I must say with zeros over the diagonal. Pois não.
Pois
não, pode falar.
A gente não está vendo sua tela agora mesmo.
Não está vendo?
Não.
Espera um pouquinho. Calma lá. Eu não estou apresentando. Eu achei que eu estava apresentando. Então, por alguma razão.
Aí vou.
Eu acho que a conexão caiu e voltou, Luiz.
Deve ter caído minha conexão e voltou. Tá. Eu peço desculpas, às vezes acontece isso.
Excellent.
Tá, agora está vendo minha tela, tá?
Sim.
Então tá.
Great.
Aonde parou de ver minha tela?
Aí.
Tá, então aqui tá bom. Tá, então
bom.
tá. Então, this is the Iwasawa decomposition, and the Cartan decomposition are skew symmetric plus symmetric. Well, this works also for complex and also for quaternionic matrices, and just must change, take the corresponding K plus S. This MMM means nothing. It's just that I forgot to revise what I was writing. Okay, what I call the hyperbolic orbits of G, or in the Lie algebra G, you take G, the capital G, any group with Lie algebra G, maybe the automorphism group is enough for everything that what works here, and take the maximal compact subgroup, which I denote by K, and which is just the exponential of K, is maximal, and I will take orbits from starting something is wrong here. I will take orbits starters on this A subalgebra, always. This is what I call hyperbolic orbit. This H is usually called a hyperbolic element. And I will consider this non-compact orbits in this semisimple subalgebra. And related to it is this suborbit, what I call suborbit, which is the compact part of the orbit, which is the adjoint of KH. This compact part, it stays in that S subspace, in the symmetric part of the semisimple algebra. And actually, it is the just intersection of the orbit with this subspace. Okay, and this compact part is a flag manifold of the Lie algebra. The group G is a material here. It doesn't matter which one, and this is the every flag manifold of Lie algebra appears as a compact orbit this way, and conversely, every such orbit is a flag manifold of the real semisimple Lie algebra. The model is written below. We take H. The A part is the subspace of diagonal matrices, and in case of SL, N, the diagonal matrices of zero trace, and the adjoint orbit is just the set of diagonalizable matrices with a given prescribed set of eigenvalues in SLN. It works in the linear group, while the compact part is just the set of symmetric matrices with the same eigenvalues. Okay, then this is the construction of the orbits. And the first remark about these orbits are that, first remark I make here is that these orbits contains two natural affine subspaces. I am keeping fixed the H, and this N plus is what I call the N above, is the set of upper triangular matrices, and this H plus N plus is an affine subspace of the subalgebra. You can do the same thing with the lower triangular matrices. You get a new affine subspaces. Well, the fact that's written here is that both of these affine subspaces is entirely contained in the orbit. So the orbit contains these affine subspaces, and let me. Well, I thought I have written here. The point is that the point about this inclusion is that think G of matrices. When you conjugate a diagonal matrix by a upper triangular matrix, the diagonal remains fixed, and you get an upper triangular with the same diagonal. Essentially, this is what's written here. There is an imprecision here. I ended thinking, when I wrote this, I was thinking H to be a regular matrix. But in the non-regular, it goes a bit different, must change a little bit this N plus and this N minus. And what happens is that this subspace, this affine subspace, it has a natural identification with the tangent space at the origin of the orbit. The origin is this H. I'm reading. The point is that when the group G, the non-compact group G, acts on the tangent space at the origin of the compact orbit, of the flag manifold. The point is that when the non-compact group acts on the flag manifold, there is the tangent space at the origin is identified with this subspace which complements this n minus complements the isotropy subalgebra. And so by this map, that you take an element of the Lie algebra associates the induced vector field, you get a vector at the origin, and this identifies the tangent space with this affine subspace H plus n minus. And on the other hand, when you take H plus n plus, the upper triangular, this n plus is naturally in natural duality with n minus. So I can look this H plus n plus as the cotangent space at the origin of the flag manifold. And more general, I start from the origin. I take translations by k, rotations by k, and so when taking these kind of rotations by k is the compact part. So I am thinking of add k as a rotation. Rotations, and then I get the cotangent space of the flag manifold. Here it's wrong. It's not. Here it should be the flag manifold here inside. This is the cotangent space of the flag manifold. Is given by exactly this adjoint orbit. On the other hand, the tangent space is also identified with the tangent space of the flag manifold is identified with the adjoint orbit as well. So the adjoint orbit, let's say it's diffeomorphic to both the cotangent bundle and the tangent bundle of the flag manifold, the corresponding flag manifold defined by this H, and both are, so to say, contained in the adjoint orbit. So we get the adjoint orbit as what I called double ruled manifold. It's like a ruled surface that contains lines, that contains subspaces, but it contains two subspaces. The example the elementary example I think always is the case of SL2R. To think geometrically, it's good to take this example. SL2R, the noncompact, with this, the first line here is a basis and take another basis. So the adjoint orbit becomes this hyperboloid. You compute this as this hyperboloid is essentially the Cartan-Killing form of the Lie algebra, and the compact part is the circle, which is this x, y, and z are coordinates with respect to h, s, and a. The basis h and s is symmetric, and a is skew-symmetric, and the double fibration from the origin comes from this computation I mentioned. When you conjugate a diagonal matrix by a upper triangular or a lower triangular matrix, you get the same diagonal plus upper triangular. Okay, I searched for some. Of course, everybody that teaches calculus knows well these hyperboloids, but I found it. Are you seeing my? I'm still alive or not? Hello.
Yes.
Okay. I searched for some. No, it's not here. I searched for some images of hyperboloids. Where are they? It's here. Well, this is quite elementary. Everybody's used to this, but the same thing. You have these lines. The red line is one of the upper triangular. The blue line is the lower triangular matrix in the adjoint orbit. Okay. Well, these are the adjoint orbits, and I will look on some geometry of it. The first point is that, as happens to any co-adjoint orbit in the Lie algebra, which in this case is the same as the adjoint orbit because I am with a semisimple Lie algebra, and the Cartan-Killing form identifies G with its dual. It has the KKS symplectic form, which is defined formally by this way, and is defined only by the Lie algebra, using the Lie algebra of G, and it's very popular. Usually people do symplectic geometry on adjoint orbits using this symplectic form, the KKS symplectic form. It has several properties in representation theory of Lie groups. These coadjoint orbits plays a central role. For us here, I will have other symplectic forms as well. This comes from natural. Well, comes naturally from natural. It will appear other kind of symplectic form, especially symplectic forms, especially for complex and simple Lie algebra. So I will talk a little bit about the so-called Lefschetz fibrations, which is are these fibrations that from these fibrations I start to look at coadjoint orbits and the geometry of coadjoint orbits. Some of what is written here was published in this paper by myself with Elizabeth and Lino, which defines what is a Lefschetz fibrations in the coadjoint orbit. So let me talk a little bit more about complex Lie algebras. What holds in the complex Lie algebra? There is this Cartan composition. I must choose U as a compact maximal compact real form of G. The maximal compact subalgebra is a real form, and its imaginary part is the symmetric part of the Lie algebra, and this let's say diagonal part is taken as the real part of the Cartan subalgebra. For instance, in SLN, this A is diagonal matrices, now complex matrices, and with real entries must take. Okay? So to get the Lefschetz fibration, it's out of order here, so I didn't revise well. In a complex semisimple Lie algebra, there is with a choice of the compact real form, there is a natural defined Hermitian form, which is defined by this expression where this capital K, capital crystallographic K, is the Cartan-Killing form, complex Cartan-Killing form of G. Above, I talked about the real Cartan-Killing form in a complex Lie algebra. This real is the real part of this K compact, and tau is the conjugation with respect to the compact real form. So it has this expression, and this is indeed a Hermitian form. It's a Hermitian form because U is compact Lie algebra, and it's a Hermitian form. You write it as a real plus imaginary part, and the imaginary part is a symplectic form in G. And the point here is that this symplectic form, it restricts to a symplectic form in a adjoint orbit. This is not immediate. The restriction of a symplectic form on the vector space to a submanifold may not be a Hermitian form. But in this case, it works mainly because the adjoint orbit is a complex submanifold of the complex algebra. Okay, so having this, most things I will talk is about this symplectic form capital omega, which is the imaginary part of omega, or the restriction of the imaginary part to the adjoint orbit. It's indeed a symplectic form. It's not equal to the KKS symplectic form. And to do some of the things, of the constructions, this symplectic form is required. The KKS doesn't work. Okay, so to get the Lefschetz fibration, the idea to define the Lefschetz fibration is to define what usually people in, let's say, Morse theory, in Riemann geometry does, is take the height function. The height function now, we fix an adjoint orbit. Now I'm writing the adjoint orbit through H naught, H0, and take the H function of a fixed H. Usually it doesn't matter. I want to take H in the S part, that is in the imaginary part of the compact real form, but since it doesn't lose the generality in taking it in the real part of the Cartan subalgebra, in this A subspace, and take this height function, which is let's see the height function. Okay, then I have this first theorem on this subject of the Lefschetz that's proved. It's proved, I think it was published in this, Elizabeth can confirm to me, it was published in this paper. Elizabeth is here, I didn't see Lino, but maybe they can confirm to me. What's the behavior of such an H function in a adjoint orbit? It's what's called the Lefschetz fibration, and it satisfies these four properties. First, there are a finite number of singularities, and they are non-degenerate. Non-degenerate means that the complex Hessian of the function at the singularity is a non-degenerate quadratic form. If you have two regular levels of the function, then they are diffeomorphic. And this third item starts with their existence. So I will change. Take that symplectic form omega, which is the imaginary part of the Hermitian form. Then a regular level is a symplectic submanifold of omega. It's in this third level, the third item, that I must take the symplectic form of capital omega, this imaginary part. With KKS, this statement is not true. The level may not be a symplectic submanifold with respect to the natural KKS symplectic form on the adjoint orbits. This is the reason why I have been trying in many instances worked with this other symplectic form. Okay, forget about this fourth item for now, because I will talk a little bit more about the singular levels. Okay, so this is Lefschetz vibration. When I didn't look at this theorem for a long time, and when I was preparing this talk, I made a Control C plus Control V in this document of this theorem, and I realized that I didn't ask before about this diffeomorphic. Maybe somebody asked me and I don't remember, but about this diffeomorphism between the level sets. The question is, are they symplectic diffeomorphisms? I don't know. I just thought now. What I can say at this point is that the proof, the original proof, the initial proof I had about this diffeomorphism is that it doesn't say that it's symplectic. The proof of the main point about this theorem is just the proof of this diffeomorphism. Is the most involved technical point, and the proof depends in showing that when I take that H, I build a transversal vector field, the Z of X, which has an ugly expression like this. And the main point in the proof is to show that this vector field, which is a normalization, essentially a normalization of a gradient vector field, to prove that this vector field is complete outside the singular levels. And this is quite technical. The proof I have here is quite technical, involving uses some of the structures of semisimple algebra in a no immediate way. So the question I just made, if the diffeomorphism is symplectic, I can say that by now I don't have the answer. Maybe some of my collaborators that is present can say something about this. I include this remark to emphasize that the right symplectic form to work is the imaginary part of the Hermitian form, because of the levels. It's desired that the levels are symplectic submanifolds, and KKS does not work. So I put something more about how is the behavior of the singularities. I said 5 or 7 or 8 minutes ago that the number of singularities is finite. I forgot to say, all this is with the assumption that the H that defines the Hate function is a regular element. I said that the singularities are finite, and actually, in this case, the singularities is a norm of the Weil group of the algebra G. This real part of the Cartesian subalgebra, it's endowed with the Weil group action, the group generated by reflections, and this is a finite group. And I wrote here this is the case for SL3 with both H and H log regular elements, and these are the singular points. I write here, we start with a matrix, a diagonal matrix with these entries, and to get all the other singularities, you permute the entries of the matrices. So the 6 points you see here are other diagonal matrices with the entries permuted according to these numbers that appear here. So the six singular. All the singularities are non-degenerate. Here is more information about the singular fiber. So a singular fiber is written this way, where this W I write here is an element of the Weyl group. It's one of these dots, the black dots in the picture above. The singular fiber has a nice description as it's the union of a subbundle above the regular set, in the flag manifold, which is the compact part of the orbit, plus those two subspaces that are contained that are contained in the orbit. Here it's write only one of them because the other one is embodied in the first part. Okay, the regular levels are more here it can see the idea of the diffeomorphism of the regular levels, that each regular level, it's in fact a subbundle. I have this bundle here, adjoint orbit, over a flag manifold. When I put K there, it's a flag manifold. And you restrict this bundle to the complement of the singular set, which is the regular set. So it's a vector subbundle. And the regular levels are affine subbundles of this. Each regular level is an affine subbundle over this regular set, the complement of the singular set. I forgot to say the singular set is contained in the flag manifold. So when I'm writing this, it makes sense. This W of H norm is contained in the flag manifold, the symmetric part. Okay. So most. Hello, pode falar.
Before you go on, so just a quick question.
Pode falar.
I'll ask the question in English, okay?
Okay.
So the typical fiber has this natural symplectic structure, right? But at the same time, you have each of these typical fibers has a natural induced metric because there's the ambient metric. So it seems to me you could ask for these two things to be compatible. So do we know anything, for instance, as to which Lefschetz fibrations actually have Kähler fibers or nearly Kähler fibers? You could ask for some compatibility between the symplectic structure you get and the ambient sort of metric, right? And you could ask, when does which properties your height function needs to have so that you get more compatibility on the typical fiber? Did you guys think about this? Is this known? I have no idea.
No, this compatibility holds always. So I mentioned only the restriction of the symplectic part, the imaginary part, but the restriction of the real part is a Riemannian metric. So you have a nice Hermitian structure on the fiber. So each fiber has an Hermitian form, which is a restriction of that H. I mentioned only the imaginary part. Okay.
Thanks.
Fine. Now I am lost. Yeah. Let me see. Yeah. Okay, thank you. Okay. So time is going. I wrote here. Well, one of the problems we posed for some time ago is to study better this vibration. So we did something. I wrote here, but I think I will skip. I skip these charts. I have nice expressions. Nice, no, they are not nice. I have expressions which are polynomial expressions for FH in well-chosen charts around the singularities. So I take a singularity and take a chart defined by an expression like this. Exponential, there is an n plus, forget about this capital N that's written here, and look only at add e to the I, e to the x, wh naught, where y is lower triangular and x is upper triangular. Then you get this defines a chart around the singularity, wh naught, and it's a polynomial chart. And in the height function in such a chart is written as a polynomial like this, which is a polynomial. The order of this polynomial is the maximal height of the roots or things like that. I can write for projective space, taking particular the projective space. In the projective space, I get an expression like this for FH. FH is the height function. Get an expression like this, which is a second order polynomial. The a's here in this expression, right hand side, the small a's are coefficients, and x and y are the variables, are the variables in the chart, are the coordinate elements, x and y. And the function is this quadratic polynomial. And of course, I can change the coordinate, this chart linearly. I can move it linearly and write FH as what is expected. Usually, people from doing these Lefschetz fibrations, they look at the function around the singularity as the sum of squares of complex variables, and it's possible to write this way. A similar approach can be done for Grassmannians. Also, the point is that projective space and Grassmannians, the nilpotent algebra that you must do is abelian. Okay, and the problem that is still open is to write in a convenient way vanishing cycles for around each singularity. What is this? Are spheres of half the dimension. It's not written here. Each sphere contained in a regular level, and these spheres vanishing to a singular point. I'm writing here x naught. Okay. An example of this vanishing cycle, it generalizes what is done in real case for Morse functions, where you have an attractor, for instance, of a Morse function. You have a sphere that vanishes to the attractor point. And you can do this, in principle, theoretically, you can do this for around any singularity, because we are in complex. You have more dimensions than just the real case. So many things, and the point is to have these spheres that are Lagrangian inside Lagrangian spheres, half of the dimension, inside each of the level of the regular levels. And I have been trying so and so to get nice expressions or get nice vanishing cycles without without a definitive success to get these vanishing cycles. So this is a problem, and but this problem suggested that work and try to get Lagrangian submanifolds in general. The hope is that if I have enough Lagrangian submanifolds in such an adjoint orb, I can see some this vanishing cycle somehow. This is the hope. Anyway, it's an interesting question to get to write the Lagrangian submanifolds. More recently, I developed a method for this, which is together with my PhD student. He finished now in February. He concluded his thesis. And Sebastian Baez, he's now in Colombia. He's back to Colombia. And a method that consists in making, take another kind of co-adjoint orbs, instead of going directly to the semisimple Lie algebra, we constructed another algebra structure, Lie algebra structure, in this subspace with this direct sum decomposition, which is the Lie algebra structure is given by the semi-direct product, not productic, as is written here. It's written as the semi-direct product of K plus S. S is viewed as an abelian subalgebra, as a vector space, just a vector space, and I have the adjoint representation of K in S, and this defines a new Lie algebra structure in G, which is essentially keeps the brackets between K and K and K and S, but the bracket between S and S, which in the usual Lie algebra structure is contained in K part, you just make it zero. This is the construction of the Lie algebra structure. Then we go to look at the adjoint orbs. Doesn't make too many sense. In the Lie algebra, in the semisimple Lie algebra, the adjoint makes sense because I identify adjoint with coadjoint. Here, for this new Lie algebra, there is no such identification, natural, because the adjoint and coadjoint orbs are not equivalent. There is no quadratic form, natural quadratic form invariant. So I must work with coadjoint orbs the same way. And the point is that I can identify G with G star anyway and get a representation of these semi-direct product on itself, which is not the adjoint representation, which is the co-adjoint representation, and this representation is given by this formula, adjoint of AX, A in K, X in S, is given by this kind of upper triangular matrices. In the diagonal is the representation of K in itself and in S. And the upper triangular part becomes from the bracket between K and S. And this is a new Lie algebra with this adjoint representation. And this adjoint representation is in fact, the co-adjoint representation of the semi-direct product. What is the point? The point is that this co-adjoint orb, it's I call it coadjoint orbitas O semi. It's not what I had there, a hyperboloid, but it's more like a cylinder. In the following sense, it's written below that this orb is now the union it's also a fiber bundle of the over the flag manifold, but now all the subspaces above a given point are contained in K. And these subspaces are image of the adjoint of the base point computed at S. So it's like a cylinder. I have the flag manifold sitting in S, and each vector space is contained in the K part, in the complement, contrary to the other that it's not contained. Okay, so I wrote here. I will be a bit faster because time is going, and I wrote here how is such subspace, and the point is that this is also a vector space, and this vector space is also diffeomorphic to tangent and cotangent spaces of the flag manifold, and with a special thing to work with it algebraically, it's easier, and we got the following theorem that we write a one-parameter family of diffeomorphisms, actually of the tangent space, and this one-parameter family, it maps this orbit to this co-adjoint orbit of the semi-direct product into the adjoint orbit we are working with. This one-parameter family of the diffeomorphism essentially amounts to construct new Lie algebras structure by deforming the Lie algebra structure. I write brackets in S, multiplying the bracket by epsilon. When I make epsilon go to 0, this goes to 0, and it gets the same direct product. With epsilon equals 1, it's in the original Lie algebra structure. At each level, it's a semisimple Lie algebra isomorphic to G. This is the point. So this orbit is a semi-direct product. And as application of this deformation, we went to look in the complex case, the same symplectic form omega. Now, I need to have a theorem to get that this symplectic form restricts to a real symplectic form on this new coadjoint orbit. And it's true. It's also a symplectic form, but the point is that these new orbits are not complex submanifolds, so it's not immediate that this is a complex symplectic form. We proven this, and it works the same way. And more than that, the deformation, diffeomorphisms, they are symplectic maps. So I can work to get, for instance, Lagrangean submanifolds in this orbit, in the simpler orbits, can get Lagrangean submanifolds and deform them to get Lagrangean submanifolds in the original adjoint orbit. Okay, so as an application, we get some Lagrangian submanifolds in the adjoint orbits with respect to the form omega by working easier in this new semi-direct product orbit. Okay, well, my time is over, and let me show you. I went to the internet, and the best picture I could find of this deformation is this. You have here in the blue, where is my little hand here? I don't know if you are looking here. This is a cylinder. This is supposed to be the semi-direct product orbit. When you click here, it starts to deform, becomes a hyperboloid. It's too fast, but you can see it becomes the hyperboloid, and the hyperboloid is the adjoint orbit. Here it goes too much. It closes the flag. It gets a new potential orbit or something like that. But the deformation is a generalization of this picture. I couldn't find a better picture, so I show you this one. So I think I must stop here. I wrote something else. I didn't, for lack of ability to compute time, I put lots of other things. So I will stop here with this deformation. Okay. So,
okay. Very much.
Hello.
Of course, we have time for questions, so let's take some questions or comments, and maybe you can ask the speaker to expand on some of the extra topics. So just raise your hand officially if you can, using the raise hand function. Otherwise, I'll try an excellent, following Elizabeth's example, you can raise your hand using the tool. Otherwise, just present yourselves in the chat. Go ahead, Elizabeth.
Luiz, but if you take the Lagrangian submanifolds, the new Lagrangian submanifolds you found, and you take their image by the diffeomorphisms with the joint orbits and look at the fibrations, do the images of these Lagrangians pass by these critical points of our Lefschetz fibration?
I don't know. we just got the Lagrangian submanifolds, but of course, the hope is to apply to the Lefschetz fibrations, but we didn't do it up to now.
Okay.
What about? I have a question. There are no raised hands. Raise your hands, people. What happens to say Lagrangian intersection numbers, right? So you can deform just a Lagrangian into your real actual orbit, but what happens, say, with the intersection of two of them if you deform them into the actual orbit? Does this process preserve intersection numbers?
Possibly, because phi is a diffeomorphism. So you get Lagrangian submanifolds in the deformation by symplectomorphisms. So the intersection should be the same. Okay, so things like these categories, what's the name, Elizabeth? Fukaya, yes. These categories of Lagrangian submanifolds that are defined all the places. I think that, yes, it's preserved, certainly, because the deformation is a diffeomorphism, deformations between the orbits.
Cool. Yeah, that's why
I don't know, Henrique, I don't know. You just asked me, I am replying by reaction. Okay, but it should be.
True, right? That would be a great thing to be sure of, because this is Lagrangian intersections are a big deal, right? It would be good if they were preserved.
Yeah. Okay. Next question.
Next question. Comments. Remarks. Daniel, you have your microphone on. Do you want to ask a question?
Sorry, those were my little kids. I'm sorry.
Okay.
No, your daughter or son, I don't know, is trying to ask a question, Daniel.
Yeah, sort of.
Sorry. No, estou brincando. I'm joking.
They don't do much symplectic geometry in Chilean kindergarten.
They don't do symplectic geometry in any part of Chile anyway, so don't worry.
Hey, come on, sometimes we do.
Não, a Elizabeth lá está fazendo.
Sometimes we do.
Maybe you're the only exception, Elizabeth, right? But maybe Enrique Reyes and someone else, but not much. It's sad anyway.
Elizabeth is in Antofagasta.
Did you know
Yeah,
that?
yeah. I mean,
by collaborator.
I know that she's in Antofagasta, but we've never met before. So
There you go.
I see. Yeah, good.
There you go. New friendships arise.
Right, we met online the first time now.
Okay, if there are no further questions, let's thank the speaker again, please. And we will see each other again in 2 weeks' time.